In this lecture, we're going to continue our discussion of arrow pushing and how we can understand chemical reactions, but we're going to focus on bond breaking instead of bond making. So getting into it, what we had talked about last time was that you could take some element with a positive charge and some element with a negative charge, and the negative will be attracted to the positive. And we'd show an arrow connecting the negative to the positive, and that would suggest that we're moving the entire atom over and allowing the electrons to engage the molecular orbital, an atomic orbital or molecular orbital on A, to allow for the formation of a covalent bond between A and B. The charge on A then decreased by 1, and then the charge on B increased by 1. We looked at a few examples of that. What I want to do is show maybe one more example, and then we'll move into some examples where we could have bond breaking. So let's imagine that A is the following, B is the following molecule. So if we have B as the following molecule, and this is ammonia, ammonia is actually a decent base, and it can react with H+. Now, this isn't a typical Bronsted base because we don't form water as a result, but we can have the lone pair electrons on nitrogen engage the hydrogen, and that will form a covalent bond between the nitrogen atom and the hydrogen atom. So we have this new bond that's formed between these two elements. And the new bond has 2 electrons, just as any covalent bond does. The source of those 2 electrons was the lone pair of electrons from the nitrogen atom. The nitrogen took with it the 3 hydrogen atoms that it started with, and now we have this molecule. You'll notice, though, that we have an overall +1 charge on the left side, and we need to have a balance of charges as we move to the from one side of the reaction, the starting materials, into the products. Now, in this case, it turns out that the positive charge is on nitrogen instead of a hydrogen atom. That allows for an overall +1 charge, and it can be accounted for by the formal charge of nitrogen. Nitrogen is a group 5 element. It has 4 bonds, and it has 0 unshared electrons. And so this is equal to a +1 overall charge, which is indicated on that nitrogen atom. There's several ways to look at this. We see an overall balance of charge, +1 on both sides. We can account for the charges in every case by formal charge calculations, something that we should hopefully get pretty soon at least, have some mastery over. And this is something you may want to practice. Now, the things that are odd, though, are we didn't start with an A and B that were both charged, okay? We have A, which is our H+, and B, which is actually our NH3. Now, it's not negatively charged, but it still has a lone pair of electrons, and that's an important point. When I have an arrow on B from a negative charge, I'm really showing the arrow from the lone pair. That's kind of awkward. Let me put those lone pair of electrons right there. What I'm really showing is the movement of electrons, and in this case, 2 electrons. And in most cases, we'll see some examples today, but for the rest of the semester, for the most part, we'll see 2 electron movement. Gosh, I should again stop previewing things. We're going to look mostly in the 2-semester course at 2 electron processes, but we're actually going to start with 1 electron processes. So it's going to seem like there's only 1 electron processes, but it's just a natural way to start kind of learning about chemical reactivity in the course. Okay, so anyway, we had a neutral base, a neutral molecule that interacted with our positively charged hydrogen, and that went to a +1 overall charge on the molecule A and B. Now, that still actually fits. That still actually fits with our B up here. And B up there, the charge increased by 1. It went from -1 to 0, and down here, we're increasing from 0 to +1, still just an increase of 1. So kind of practicing this and seeing the patterns that form as you form covalent bonds will be really helpful. Now, I said I wanted to get into some processes where we can look at bond making and bond breaking. And last time we looked at a pretty difficult example where, at least the first time you see it, kind of a cumbersome example where we had our OH minus interacting with HCl. Now the negative charge actually engaged the hydrogen, and the hydrogen said, you know what, I can only have 2 electrons, either sharing with chlorine or sharing with oxygen, one or the other. If oxygen's attacking, I'm going to push the electrons onto the chlorine atom. And so what we showed was a simultaneous bond making and bond breaking event. Now, for us to get better at this, we should slow down and look just at bond breaking events and not look at kind of a concerted process where bond formation and bond breaking are happening in concert. So to do that, what I want to do is define bond breaking events. And there are 2 types of bond breaking things that can, bond breaking events that can happen in chemical reactions. There's what we call heterolysis. Now, heterolysis is the most common. And again, I want to be careful. It is truly the most common type of bond rupturing event that we see, but we're actually going to start with the other form that I'll get to in a moment. So in heterolysis, what we have is if A is bound to B, we are going to show the movement of electrons from being shared between A and B to then being localized only on one element. So we're going to push the electrons from A over to B. What happens when you do that is you gain a positive charge on A and a negative charge on B. This is the opposite of bond formation that we saw before, where we had the electrostatic attraction between A and B, and we showed that by having the lone pair of electrons add to A. That decreased the charge of A by 1 and increased the charge of B by 1. Now the exact opposite is happening. Here we have an increase in charge of A as we're losing those electrons. It's becoming more positive by a unit of 1, and B is decreasing in charge by 1. And so we have an overall balanced charge. Now the reasons sometimes it's a little bit hard to see because we're moving 2 electrons. Why are the charges only changing by increments of 1? That comes out in the formal charge calculations actually. But this is called heterolysis. Now, where it gets its name starts with an important term that many of you have probably seen, but let's just mention it anyway. So lysis is to break down. And I'm sure there's probably a better definition, but that's what we need to know. Lysis means break down. So in heterolysis, we break covalent bonds such that each atom has a different number of electrons. And so in A and B, they both have, each element shares 2 electrons. And then when we break the bond by heterolysis, we're going to rupture the bond such that A has 0 electrons and B has a lone pair. Now, A could have other electrons, but in terms of from the covalent bond, from that sharing of electrons that we saw, A has 0 electrons and B has 2 electrons. Okay, so these are different numbers, and that's where we see that hetero or different prefix to this lysis event. So different electrons. Okay, so and the electrons that we care about counting are those electrons that were once shared to make the covalent bond. Now this is in contrast to the other type of bond breaking event, which is homolysis. In homolysis, we again see the suffix lysis, but instead of hetero, we have homo, which means same, and that implies the same number of electrons after breaking the bond. Okay, so in homolysis, we have to sort of move the electrons in opposite directions. We have to get to a point where we have A with one electron and B with another electron. Because if we split the electrons in the covalent bond such that each atom gets one electron, then the number of electrons each atom gains from the ruptured covalent bond is equal. We have the same number of electrons from each how about just on each atom? I realize that A and B are different, and so they probably have different numbers of electrons. It's my guess, but different numbers of total electrons. But what we're worried about is the number of electrons that they gain or lose as a result of the covalent bond breaking. And so in this case, they once shared two, and now they each contain one of those electrons that were once shared. This is an unusual arrangement, this element with only one unshared electron. It doesn't have these electrons paired up. And that brings us to a new topic in the course called free radicals. So with free radicals are molecules and molecules slash atoms where one element, there can be many elements, but it gets complicated when there's multiple elements. So let's say at least one element has an unshared, and that means unpaired. It's a weird symbol. Valence electron. Okay, so an unshared, an unpaired valence electron. And so that would be like this. So that's what a free radical is. I'm sure many of you have heard of free radicals in the context of health and that sort of thing. And that's exactly what they're talking about. There are important free radicals out there. Oxygen, it turns out, is actually a free radical, and we harness the energy of its free radical to do the things that it does, the oxidative processes in our body. And number two, the other thing is these elements then have an odd number of valence electrons. Now, these 2 points are not too different. It turns out if you have an unshared or unpaired electron, you then very likely have just an odd number of electrons. There's a specific example of this where if you take chlorine in nature, it's actually bound to itself. So chlorine gas, which has an elemental composition of just chlorine atoms, is actually a bunch of Cl2 molecules. So many of the halogens, like fluorine, bromine, chlorine, iodine, come as diatomic molecules. That is, there's two of each element bound to each other. If you look at this molecule, both of the chlorine atoms have an octet. They have 6 electrons as lone pairs, and then 2 electrons that are shared between the 2 elements. Now, it turns out that if you, and we'll talk about this quite a bit, if you expose this to heat or light, we have our delta, which is the old-fashioned symbol for fire, implying heat, or light, we can actually split this molecule in half to give chlorine radicals. And you make 2 of them. Now, what happened here was the diatomic chlorine, the diatomic halogen, underwent a homolysis process, and it gave rise to 2 chlorine radicals. So again, this was homolysis. Okay, so again, with homolysis, we're breaking the bond such that the 2 shared electrons are split in half, and one goes to one element and one goes to the other element. Each of the resulting elements now forms a free radical. If you have one element in a giant molecule that has an odd number of electrons or one single unshared and unpaired electrons, those two things are actually the same. If you have that scenario, then you have a free radical. And that's just something to be mindful of at this point. They do have certainly interesting properties. Now, what I want to note about the chlorine situation is that the elements in this case are actually neutral. So unlike with heterolysis, where we form two charged species, free radicals are often neutral in charge. That is to say, you oftentimes don't have a charge. And so for the most part, I mean, you can introduce radical cations and radical anions. You can have those, but they're actually formed by different processes. So homolysis gives rise to neutral elements. Now, when we see this, that kind of makes sense. So if we have chlorine and chlorine, this is overall neutral. Now, if we rupture that bond to make two chlorine radicals, we should also be overall neutral. Now, both elements are the same. And so in this case, it doesn't make like they're the same in every way. They're the same atom and they have the same number of electrons because they each gained one electron. So they should both be neutral. We can't have one elemental combination, one combination of protons, neutrons, and electrons sometimes have a positive charge and sometimes have a negative charge, okay? Now, we can actually compute this, determine this, using formal charge calculations. If you recall up above, I said that we had 6 lone pairs of electrons and then 2 electrons were part of a covalent bond. We split the covalent bond in half. Each element now has 7 electrons. Chlorine in this case is a group 7 element, so we're going to take 7 minus the number of bonds, which is 0, minus the number of unshared electrons, which is 7, that's equal to 0. So no matter how you spin it, the atoms are neutral as a result of homolysis. So we don't form a charge. It doesn't seem too bad, right? Homolysis, they get the same number of electrons after breaking the covalent bond in half. Heterolysis, they get opposite numbers. One gets all of them, the other one gets none of them, okay? So those are kind of the two principal bond breaking events. Now, what happens though, is that our curly arrow notation takes a hit. We need to develop new curly arrow notation to take advantage, or kind of not take advantage, to clearly communicate that we're moving only one electron and not 2 electrons. So 1 electron processes require different curly arrows. Okay, because we need to accurately communicate where the electrons are going. The electrons are going to do their thing. The arrows are just things for us to communicate to each other. And so what we want to do is find a way to clearly communicate when it's a 1 electron process, such as homolysis, versus a 2 electron process, such as heterolysis, or when we're forming covalent bonds by attracting positive and negative charges. Okay, so if you recall, we had the original arrow, and I'm going to have mine very curly. So this is a 2 electron arrow. Now what I want to point your attention to, and it's not going to make sense why at this point, is the arrowhead. We just have a standard arrowhead. Now what I want to do for 1 electron processes, so this was for heterolysis, and I'll have some sort of color matching for people that review this later. In the case of homolysis, okay, we're going to change the arrow slightly. We're going to delete half of the arrowhead. So we have a half arrowhead. And these things are a little bit cumbersome to draw at first. You would think they wouldn't be. It's just a typical arrow. You cut off half the head. But when you're working fast, you get to that arrowhead and sometimes it gets a little sloppy. And we're trying to be all about clear communication. So half arrowhead indicates 1 electron is moving. So a full arrowhead moves 2 electrons, such as both electrons in the covalent bond. But a half arrowhead suggests that only 1 electron is moving, such as in a homolysis process. So let's look at some examples of these. So if we have A and B, we're going to move both electrons over to give rise to A and B, where B has the lone pair of electrons because the arrowhead suggests that 2 electrons go to B. It's the arrowhead that indicates where the electrons are going, whether we're having electrons doing attacking or whether we're rupturing a covalent bond. The electrons are going to follow where the arrowhead is. So if we had A and B undergoing a homolysis process, what we're going to do is not put 2 electrons over to B, but we're going to put 1 of the covalent bond electrons over to B. So with one of the electron, if only one of the electrons are moving over to B, we're going to show that as this half-headed arrow. And the thing is, though, now we need to show the movement of the other electron. The other electron is going to jump over to A. So I'm showing the movement from a bond to an atom. That just suggests that now, instead of being shared between 2 elements, the electron is going to be localized on A and B. Now, for heterolysis, we had to be mindful that we had a charge, plus where we lost electrons, negative where we gained electrons. Now, in the case of homolysis, there's no charges. We start at overall neutral, we end overall neutral. If you find elements that do these types of things, they will not be charged. There will be no change in charge unless we started that way. That is to say, when I said you could have a radical cation or a radical anion, that is an odd number of electrons on an element that has a charge, it's because it started with a charge. When you do homolysis, you don't change the charge of the element. Okay, and I forgot to draw my reaction arrow here. But so we have reaction arrows and we have curly arrows. We have 2 types of curly arrows, the standard run-of-the-mill typical arrowhead showing the movement of 2 electrons now, and we have a second type of arrow showing the movement of 1 electron arrows. So the half-headed arrows okay, so I've got my half arrowhead here. My half-headed arrows are called, they actually have a fun name. It's called a fish hook arrow. And if you look, they kind of look like the end of like an old school fish hook, you know, without a fancy lure and that sort of thing. And so these are fish hook arrows, and they depict / indicate the movement of 1 electron. So when we're breaking a covalent bond, we need 2 arrows to show the movement or where each of the electrons end up. When breaking a covalent bond, spell that right. We need 2 fish hook arrows. That is to say, A and B goes to this and this. 2 fish hook arrows. Okay. So what we did was we spent some time talking about how to indicate the direction in which electrons move. These nuances, this nomenclature, it's not going anywhere. Super useful all the way through your chemistry curriculum, whether it's organic chemistry 1 or like your last semester of some advanced level biochemistry or synthetic chemistry course. We're going to use curly arrows the entire time to show the movement of electrons, because when you move electrons, nuclei come along for the ride, and atoms start to change position and bonds start to switch around. And when that happens, matter gets transformed. So really, as kind of you know, it's just another one of these things in this class where we have a model that at first seems strange, but is ultimately very powerful. And there are so many models, and I've really tried to just filter out and use the and teach you the most useful ones, the things that have a long half-life in your careers. So, but of all of them, pushing electrons with curly arrows and showing where electrons will want to end up on molecules is by far one of the most useful skills you'll get out of these 2 semesters of organic chemistry. And again, if you want to get a jump start on this, I really recommend the book Organic Chemistry as a second language, first semester topics. It goes over electron pushing in a lot of detail and actually gets you ready for second semester topics. But anyway, that'll do it for this lecture. In the next lecture, we'll practice some of these strategies and try to predict the product of certain types of bond rupturing, bond breaking, and homolysis, heterolysis. What do the products look like? An important skill.